Thank you. Before we start, I would really invite you to sit closer to me because we have some live coding examples and we have tried really hard to scale things up, but there's so much we can do. So, hello. My name is Mikoláš from Future, and I'm here to talk about scripting in LLDB. In this session, we will discuss why care about LLDB, what is LLDB. We will set up environment for scripting, explore the scripting API, and use it to create a custom type descriptor. This session may be challenging for beginners, but feel free to catch me later, and I'll try to clear things up. So why care about LLDB? As Swift is getting more mature, there is a growing code base of Swift code. Also, with rise of generative AI, it's more likely our workload will skew towards fixing bugs instead of writing new code. We will also likely encounter more complexity in the software itself with introduction of more multi-platform solutions. And we also introduce bugs of our own. Our ability to orient and code faster is crucial. In this regard, LLDB can have a huge impact because it allows us to observe the code as a living thing instead of pages of code. So often when I need to familiarize myself with a code base or a problem, I start at a certain point where something important happens. From that point, I either need to figure out why it happened or what happens next. For example, suppose I have an HTTP error message on the screen, and I need to figure out which part of the code initiated the API call. Or there is a button on the screen, and I want to determine what happens if I press it. LLDB can help us with both of those scenarios, but in this session, I will focus on trying to understand the past. One of the most frequently used features of Swift are escaping closures. We often create a closure, store it, and call it much later. The disconnect between when the closure was created and when it is used makes reasoning about such code especially challenging. In this session, I will demonstrate how LLDB scripting can help us track down closures to where they were created. So now let's talk about what is the LLDB. The LLDB is a program which is able to manipulate other programs. It attaches itself to that program and is able to pause its execution, read its memory and registers. It can also write into the memory of the traced program, even into read-only and executable memory. It can write into registers, even into program counter. It can load additional libraries and much more. Now the interesting part. It's internally divided into two components, LLDB and LLDB server. Those two components can run on different machines and talk via a protocol called GDB remote. And now I would like to pause a little bit because the green part, the GDB remote stuff, it's really interesting, and I have actually found an article a while back about how this thing happens, and you can actually dump it yourself. But the article since was removed from the internet, and I have the PDF, so I will show you at the end the proof that I have it, and you can have it too if you ask me. So the LLDB server uses API called ptrace to trace the process we are interested in. How we can interact with LLDB? So we can use graphical user interface, such as Xcode. We can use command line interface. And for greater convenience, we can set aliases for commands, but only one command can be executed at one time by an alias. There is also an API for scripting. We can either use script to run the LLDB itself, or we can use it to create a custom command or data formatter. As for the data formatters, those can be used by the GUI application itself, such as Xcode. In this session, we will see an example of a data formatter. Now let's focus on the scripting and the API. The scripting is done in Python. I, as a Swift developer, don't like Python very much, but there's no way around it. I have checked. If you are more comfortable with C++, you might be in luck. But I didn't find a way how to load it into the LLDB yet, so Python it is. Coming from the world of Swift development, I strongly rely on types, and Python is known for its approach to typing, or lack thereof. But it turns out that we can use types pretty similarly to what we might be used in Swift. However, this will require some extra labor. We will need to set up a proper IDE for this purpose. And I have picked Visual Studio Code just because I have it on my computer installed. You will need additional setup. You will need extensions Python and Pylons. And then you will need to set up those extensions. And you will need to export this specific variable into your ZSHRC. This is environment variable Python path. And Python uses this variable to locate more modules. And in the Visual Studio Code, you need to go to the Pylons extension setting and enable type checking mode to standard. This will provide you with type hints and type checking. And now we can create our first script. So first thing, we will need to import module LLDB. If your IDE highlights this line, double check the ZSHRC file and the Python path is set correctly. Try to restart your computer. This is tricky part, and yesterday at the workshop, we actually needed to do some workarounds, so this might be a little tricky. We will also import type hints from Python for optional and any. We are not using them on this slide specifically, but we are going to use them down the road. And next, we define a function with this precise name. This function will be automatically executed by LLDB when the script is loaded. Everything you print from the script will be passed to the LLDB console. So it's not over yet. When we want to import our script to LLDB, we need to use this command script import with absolute path to the script, and we can place it into an LLDB init file in your home directory if you want the script to be loaded immediately when LLDB starts. And when we start the LLDB, you should see this output on the screen. So I will show you an example. Can you see my terminal? I believe so. I hope so. And first, my home directory. I will show you my ZSHRC. Okay, so there you can see that I export the Python path and append the path to the LLDB module. And I have also prepared the script from the slides. And I will show you how to configure the extension. So let's close this and this. And go to your extension pane. Find Pylons. Nice. And I have it already installed. And then there should be a cog on the screen, but probably my resolution is too high, so I'll use this one instead. Go to extension settings. And the setting we are looking for is almost at the bottom. It's over here. And you want standard, you don't want strict, because the LLDB API is not well typed, so strict setting will just complicate things. So now we can close those things. And you can see that I'm importing my LLDB. You can see that how I will open the documentation. There is also documentation available for other types and methods. And now I want to launch LLDB and execute this script. So I will copy an absolute path to this file, open the terminal, launch LLDB, type command script import, and you can see hello. So this works. And we can go back to the slides. We have already seen one type defined in the LLDB API, but now let's explore it in more detail. I will show you 6 most important classes and highlight the most important competencies of those classes. This class we have already seen. It's called LSB debugger, and it represents the debugger itself. It can create so-called targets. We will discuss them momentarily. The most important command the SB debugger provides is handle command, which accepts string as a parameter and executes it as if you would type it into the command line interface. The next type is SB target. Target represents a program running in the debugger. It allows us to inspect global variables, create breakpoints, and explore symbols. It can launch process, load core files, or is used to attach to an existing process. Target is associated with process, but it may exist before any process is launched. The SB process object represents a process running in your operating system. It has access to the memory of the process and allows you to read and write into it. It contains one or more threads. Each thread is represented by an SB thread object. You can use the SB thread object to do jumps, essentially right into the program counter, step around in code. As you would probably expect, each thread has its own stack. Individual function calls in the stack are called stack frames. And those frames are represented by SB frame. When we look for variables, we are doing so from certain stack frame. This is also true for evaluating expressions. The SB frame allows us to read and write to registers, but registers are only valid for the topmost stack frame. Unfortunately, the LLDB API, as I said before, provides no type hints, so we can either find those types ourselves in the documentation, or we need to guess. The API can also return instances of objects which are not valid. So almost all objects have this function is valid, which you need to call to check whether the object you are working with actually functions or not. And there is also one important type I would like to mention, and it's called SB value. It represents variables, registers, and results of expression. And now we can move to the scripting. Just to reiterate, our goal is to track down where a closure of interest was created. So let's look at a simple closure. Notice that there is a capture list. It will become important later. Now let's look how closure looks in memory. Closure is essentially a pair of pointers. First pointer points at the function, the code of the closure. The second pointer points at the capture context. Since closure can manipulate variables from surrounding code, it needs to store them somewhere for later use. This somewhere is called capture list and is often constructed implicitly. But sometimes, for example, when we need to capture some references weakly, we need to do so explicitly. We store the list as the capture context. The context can be nil, but if not, it must be stored on the heap and must work with automatic reference counting. We can use the context pointer, and with some help from Xcode, we can locate its creation. In Xcode, there is a tool called debug memory graph. We can launch it using this button, and we can use it to inspect all heap allocations, but that's not all. If we enable option malloc stack logging in our scheme editor, we can use debug memory graph to get all allocation backtraces of any heap object. We need to paste the address of the heap object into the filter in the left panel. And in the right panel, there is the backtrace. But we have an issue. If we try to inspect a closure at runtime, we currently get this output describing only the function pointer, not the context. Now we are going to implement our custom type description for closures, which will give us not only the function pointer, but also the pointer to the context. We will start with some utility functions. When I create LLDB scripts, I like to implement a set of utility functions first. Keep everything compact. I consider this approach not only more readable, but it's also a convenient point where to add type hints for Python, which is important for better orientation in more complex scripts. What we see on the screen is a small utility function which reads memory. Remember, memory API belongs to the SB process, so we provide it as the first argument. We also need to know what memory address and how many bytes we are going to read. And then we return optional bytes object. Bytes is a built-in Python type. Firstly, we initialize the SB error object, into which read memory function will store an error if it occurs. It's done this way because under the hood, Python API wraps a C++ library in which this is a common pattern. After we have everything ready, we can call the read memory function and verify whether we are successful or not. But for our convenience, it is also useful to create a function which reads only 8 bytes from memory and returns them as integer. It calls our read memory function. The string argument literal signifies how bytes are ordered in the bytes array. Next, since we can read memory, we can create a function for printing our Swift closure. First, we get an instance of SB process, so we can pass it down to the functions reading memory. And we need an address where a closure should be located. We use our write 8 bytes function to read 2 consecutive pointers from memory. We return formatted string from this function, which contains pointers we read. Function nice hex format is my function which makes hexadecimal strings from numbers, and I will show you later. And now the most important function we have yet seen. This function is called by LLDB whenever it wants to format a value. We need to provide this specific argument. We need to provide this specific arguments and return values. The SB value instance refers to the variable we want to decorate. The string we return is the string which will be displayed by LLDB, for example, in the graphical user interface. First, we need to get reference to the process so we can read the memory. We can do it by asking each individual object to give us its owner. But remember, the API can return instances which are not valid. We always need to check validity prior to making any call on those objects. I have shown only one example due to the space constraints of the slides, but I do it for all. By calling getLoadAddress on the value, we can locate the value in memory. Where should we perform the memory reads? And then we will verify that the value, in fact, could be a valid closure by verifying the size of the value in bytes. We would expect that the closure would be 16 bytes long, but for some reason, LLDB thinks the closure is only 8 bytes long. With all arguments prepared, we can call our printing function. Lastly, we need to teach LLDB what types we want to format with our new formatter. For this purpose, we will modify our init module, which runs whenever the script is loaded, and instead of printing hello, we will execute this command in the debugger. The command is named type summary add. Then we need to specify that the formatting is done via Python function. The function is referred to as the name of the Python file, appended with dot, and the name of the function. But the most important thing is the last argument. We tell the LLDB that we want our formatter applied to all types conforming to a provided regular expression. For better clarity, I have divided the regular expression using colors. Blue part specifies that we need a whole match. Yellow part represents the parentheses and arrows, which indicates closure. The red part says that inside of the parentheses can occur any string of letters, spaces, dots, and commas. This is obviously not a complete example for any generic closure definition, but it fits my purposes for almost all the cases I go into. And now let's look how all of this works together. So I will open, sorry. I will open the example. And show you the script. I will probably enlarge the font, or is it readable? I will try to. It doesn't matter. You have seen all of those things. I just want to show you. So here is our read memory function, read 8 bytes function, our closure summary, and print as Swift closure, and nice hex format. Basically, it either reports invalidate, null, or hex, and our init module function. Now, before executing the script, I will show you what I see before my formatter was applied. So this is the case I was talking about. I'm sorry, I can't make this any larger. I will try to focus. I have a breakpoint at a certain point in my code, and I want to learn where this closure was created. So basically, this is what I see. This is what I see now. You can see that there is a nicely decorated function pointer, but not the context. And now I will do the same thing as I did before. I will copy this path to the script and type, and I will, for your convenience, I will try to enlarge this. Command script import. And you can see we have our formatter installed, and now I will use frame variable. So frame variable configuration dot. Yes, thank you. Configuration dot action. Yes. And now you can see here is our custom function pointer and context descriptor. And I can take this text. And invoke memory graph. And I will paste. Oops. No, please do what I want. No. I will paste it here. In the filter, I can highlight it. Here it is. And I will try to, sorry, I can see this part of the screen. I will try to open this left pane, and here it is, the backtrace. So I can click on an individual frame, and it moves me in my code explorer. And I will try to enlarge it back. And if I continue my execution, you can see that Xcode actually now uses our custom formatter, so you can have it working passively. If you modify your LLDB file, you can have it all the time without needing to type anything. So let's head back to the slides. Since KMP is a significant topic of this year's mdevcamp, I will mention an interesting connection. And there is a support package called Kotlin Xcode, which adds Kotlin syntax highlighting to Xcode. It also expands debugging experience using set of LLDB Python scripts. If you look closely, data formatters for Kotlin is one of those provided features. And now to wrap things up. I would highly recommend you this book, Advanced Apple Debugging and Reverse Engineering from Codeco. It was the major influence which pushed me further. And it was recently updated for new Swift and new Xcode. So now it's actually a great time to get started. Also, I was using ChatGPT when I started with my scripting, and I was using it to get more hints. There is not that much public documentation about LLDB scripting, not that much examples or tutorials. So when I ran into the into a corner, I tried to use ChatGPT to provide me with some hints, but it lies as I stated in the slides. But with your development environment properly set up, most of those lies are caught actually by the type checker. So I highly recommend you to get this working. And there are few repositories which contain examples of a lot of LLDB scripts. Those examples are primarily meant for UIKit, but I recommend you nevertheless Facebook/Chisel. And there is also a repository which has nothing in common with LLDB, but contains a lot of function calls to Swift runtime called virif/runtime, which you can actually use from LLDB if you want to try some new things. And basically, in this talk, I have provided you. We have looked at basic types provided by the LLDB API. We have set up a proper developer environment. We have looked at real-life use for LLDB. And I have shown you additional resources I have been using during my study. And I am using those resources to this day. But we didn't discuss arguably more powerful and exciting feature of LLDB, the expression evaluator. I would encourage you to explore my repository of LLDB scripts, which contain an interesting application of the expression evaluator. Since we have some time, I would also add that I have intentionally didn't use expression evaluator in my formatter. And why it is? It's because expression evaluator takes a lot of time to evaluate your expression. And if you have it in your data formatter, the data formatter will be invoked by Xcode. And so each time you will pause the execution, a lot of expressions will be evaluated by Xcode passively, which is something you don't want to do. OK, so here is my GitHub, here is my LinkedIn, if you want to get in touch, and thank you. I will accept your answers and accept your questions and try to answer. And if we have some time after your questions, I will show you the PDF file I have promised.
That's a smart way how to attract people, promise a little bit of cake at the end.
Yeah.
So we have many questions, but we have enough time, so let's go through them. So do you have a repo of your LLDB script?
I do. On my GitHub. I will feel free to catch me later. I will show you in more detail.
Yes, obviously. Can you give us some other real-life examples when to use LLDB scripting?
I can. I have those examples written in here on the papers. And it's because yesterday I had a workshop on this topic, and we used expression evaluator. And with this expression evaluator, you can do really powerful features. You can create your own analysis programs. You can do. I didn't. Conceivably, you can even use LLDB as your instrumentation framework. Conceivably, I haven't done it myself, but it would be an option. So really, there is almost no limit to your imagination. You need to. The most important thing with LLDB, you need to be patient, because sometimes LLDB doesn't behave as you would expect. And so you have to constantly think about workarounds. And if you have a workaround which solves your issue, just use it. Don't try to dive deep into why your assumption about LLDB doesn't work, because LLDB is essentially even more complex than compiler itself, because it contains compiler and does a lot of things. So just use workarounds and have some patience when you develop those scripts.
Okay, how does the debugging of the scripts work?
Okay, that's a great question, actually. And I would recommend you again the book from Codeco, because you can debug your debugging scripts in the debugger. It gets really meta sometimes. On a personal note, when I was diving into the LLDB code base, I built LLDB to debug it itself. So you can do those things. But yes, there is the possibility to debug your Python scripts. And in the Codeco book, there are a lot of examples how to do so. And I will really encourage you to buy it or ask your friend to share it with you to look for those examples of debugging scripts. Also note, you can't do it in Xcode. Xcode will kill your process if you try to do so, so you have to do it from terminal.
Yeah, the article, you will provide it at the end, hopefully. Another question. Does LLDB has access to debug symbols? For example, get more information about the memory address?
The LLDB has, regarding the traced process, if you have access to the debug symbols, the LLDB utilizes those debug symbols to provide you with all of those things like frame variable we have shown you. I have shown you, sorry. So in that sense, yes, if you have the debug symbols at hand. If the question is whether you can have access to debug symbols of LLDB itself, LLDB in debug build takes, I believe, 30 gigabytes of memory to run, so no. But you can build your own LLDB. It's not that hard. You just need a lot of memory and a lot of time. OK? Is it possible to debug LLDB scripts with LLDB? I believe no, because you need a Python debugger to do the Python debugging.
OK, with a smiley. Can we write scripts separately for LLDB and LLDB server? For example, server LLDB will feed addresses, while local LLDB can utilize code knowledge.
I will read it again, sorry. Well, the LLDB server is more of all the functionality provided to you by LLDB, almost all the functionality is going through the LLDB server. So the LLDB server provides the LLDB client, so to speak, with a data source about the process. So you can conceivably create your own debugger, which connects to the LLDB server via the GDB remote protocol. So in this sense, you would be writing your own debugger, if I understand the question correctly. But the LLDB server already provides the LLDB doesn't know anything which the LLDB server doesn't tell it. So in this, if you would use this question as a statement, I would say yes, basically. Yeah.
We'll see. Maybe it's a topic for the break.
Yeah.
And the last question, is there a way to automatically import scripts at the start?
Yes, you will need to create .lldb init file in your home directory. That's the default path where the LLDB will search for it. And you can type all the commands you want to execute at the start of every debugging, not session, but start of every debugger. Whenever you start the debugger, those commands will be executed. Sorry. OK, now I have promised the file.
Yes. You still have about 5 minutes, so.
5 minutes.
Yeah.
Yes, thank you. I will, since I have some more time, I will merge my my monitors so I can see better now. Great. And I have this. Yes. I have the PDF over here, and it's actually somewhere on some Chinese website. So you can search for it yourself, but this is what you want to search for: how to make LLDB a real debugger. This is actually an article that describes a function which was based on this article implemented to LLDB. Essentially, breakpoints were not really hardware breakpoints, but this article will take you. It was written in 2019, so it might be slightly out of date in corners, but it will take you on a way to build your own LLVM and LLDB on your Mac. But that's not the thing I will want to show you. You can enable logging in your LLDB. And there are some bit masks, essentially some filters you can apply it on those logs. And in your console or something, you can read what the debug server does and how the communication works. And then you will see exactly what memory is written to, what bytes are written to, essentially what the debug server does to the process, and also here how the communication between the debugger, the LLDB debugger and the LLDB debug server is conducted. And the GDB remote, GDB remote refers to the GDB debugger. So there is another debugger called GDB, and guys from LLDB thought it would be more sensible to just use existing fine debugging protocol instead of creating their own. Yes, here, log enable GDB remote packets, and now you can see this is how the communication is actually conducted. And I wanted to mention one thing, since we are talking about the GDB remote protocol. I will jump here. You can remember I have shown you that there is the ptrace API, and again, I will show for the Codeco book. In the Codeco book, you can actually learn how to observe what the ptrace does to the process. So if you are interested in this, you'll find it there. So thank you.
Thanks. So